Action. All right. I have to put my cup of tea down. So, where we left off, we just finished this duva that draws our separation between our rectangle and our circle, and if we hit the spacebar, they separate out. And the problem that we ran into, well, it's not so much a problem, but we've come to the point in the programming where we have this situation. We have a circle struct and a rectangle struct. We have a circle list and a rectangle list, and we've got this funky toggle between them here. And then if we scroll down to do separation, we have this block of code for rectangles. We have this other block of code for circles. And both of these take some shortcuts, particularly the circles one. But then we've had to go ahead and make sort of the generic one that separates either, and it takes an array of axes, which to do, we should probably fix up the allocation there at some point. So we might do that once we've fixed up the circles and rectangles issue. And so the place we are trying to get to, and of course we have a similar situation with the drawing code, the place we're trying to get to is a place where we just have struct shape, and we can just talk about shapes. And so let's go and look at how we might deal with that. So already we're doing what you describe as compression-oriented programming, which is that idea from Casey Muratori. Which is sort of the opposite of doing object-oriented programming. So rather than trying to design all our objects up front, we've gone ahead and we've organically built up, okay, we've got a circle. Then we've said, oh, we also want rectangles. So we've built up circles and rectangles, and now we're in a position where we might be like, oh, we've got all this code, let's stop adding new features. And you could kind of say refactoring it is what we're doing, but it's not a great term, because I think it gets misused for just sort of, I don't know, massaging the code in a non-useful way, whereas what we're doing is actually is actually useful, which I guess is a...
I think refactoring has the baggage of specifically being about test-driven development, right? Like red, green, refactor. So you write a bunch of broken tests, and then you make them green, and then you change whatever you want, and then make sure they're still green. I guess it's sort of like regression type of pattern. So I can see how we're doing something a little bit better than that. I don't think, that's religious, but I don't think a lot of people do that anymore. Yeah. Yeah, refact. I don't know. I think, but there's definitely a design aspect, right? So all you're saying is that we're gonna do the factoring down into a high or up into a higher level of abstraction, I guess.
Yeah. So,
or are we? Is it another level of abstraction to say shape? Is that fair? Or are we just using a different data structure that is that like reduces, as in compresses, the amount of code we have to write? Because I don't know about, like, abstraction layers are another bad term too, right?
So yeah, we'll get into exactly what we are and are not abstracting, but largely we won't be abstracting much, but we will be making it so that the this code, because we have, and to a certain extent we had some upfront knowledge of the fact that this is what we're going to do, but it's like once you get to this point, a lot of this is kind of similar. I guess there's this stuff here with the top left, top right, and the circle projects slightly differently as well. but we're taking those differences and we're making those the core things because we've got all of this other code for actually doing the separation. And we know that, okay, we have two shapes here, and we're probably going to want more. Like we're probably going to want like struct. Like if it was just rectangle and circle and we were sure about that, we might do nothing. But once it's like, all right, we have a polygon and we probably want some other stuff in there, so we might start thinking about this now. Is a good time to do this. But the sort of the point that I'm getting to is it's better to do, to start down this path and then be like, okay, struct shape, rather than what we might do with object-oriented programming, which is like we add struct shape together. So let's, I'm just going to make a new file just for scratching notes, new item. So I'm going to call this object-oriented coding.
Your affiliation is not subtle.
So you can imagine, I'll bring my comment with me. Okay, so you can imagine if we're in an object-oriented world, we're doing like this massive design up front. We're like, oh, well, we're going to need a shape. So we're like class shape. And then, we'd be like class rectangle extend shape. And then we'd probably be like class circle extend shape. And then we'd probably be like, all right, class, oh god, we've got to add, a polygon extend shape. And you can sort of see where this is going. It's like, well, maybe we want like a triangle, but it's like, okay, well, is a triangle and a rectangle, is that just a different kind of polygon? And also, so we can do a shape that looks like, for example, this. So we've got rectangle, we've got circle. We could add a shape like, for example, this, or a shape like this. And all of a sudden, like our nice little class hierarchy that we've been carefully designing, what the heck do we do with this thing? So this is like this is like a really concrete example about why object-oriented programming is not a good plan, because you run into these situations where you don't have this nice like shape hierarchy where it's like, okay, we've got circle, and you've got polygon. Perhaps you might have this, and then if you feel like you're being really clever but you're really not, you might go ahead and be like, okay, polygon. Well, we have a rectangle and a triangle or something, or possibly if we're actually being smart about this, a regular polygon, and that lets us do some optimizations. For example, like actually no, it wouldn't be a regular, it would be a parallelogram. You could just have two axes rather than needing four axes for every side. So you might feel like, oh, look, we're making this massive optimization because we're saving a couple of axes. But in reality, we've got, paintbrush please, we've got this sort of mess of this class hierarchy. And we have no sane way to handle this because, it's both of these. And we're sure as hell not doing multiple inheritance because that's we can't even do that in C#, but it's just a disaster.
you can rewrite the MSIL to do mixins.
Oh,
let's not think.
Yeah. Oh Christ.
I've been some places. I've been some dark roads I can tell you about. But yeah, you're right. In general, it's discouraged by not being a language feature.
So. So you can sort of see the way we've approached it just by being like, well, let's make all the code for the circle, and then let's make all the code for the rectangle, and then sort of find the commonalities is going to work a lot better than trying to do this all up front and starting here. So let's sort of look at what you might do. So like if you were designing up front, you might be like, well, I need a list of axes. So it's like, all right, list vector 2 axes. Also get axes. And then that would be virtual, of course, because you'd have to... I'm just like, what's the keyword for this? Because it's like, I don't code like this normally. So you'd have to do that, and then down in... actually, it'd be struct. And then down in rectangle, you'd be like, override that, and give it an implementation. And then you get down to circle and be like, get axes. And if you recall, when we actually get the axes for the circle, the axes that we're getting are... Where are they? Yeah, here they are. They're derived from the thing we're colliding against. So already we've got this issue here where we've come up with this interface that doesn't work because we were designing it up front, and there's like, we've got to add a circle in here. So already we're going to have to go through, we're going to have to modify this. So actually that's going to have to take a shape. And so we've broken the interface, which is, lovely. And like, I can't do much more other than just sort of point to this and be like, see where the problem is. I know. Do you see how this is sort of starting to become a mess?
Yes, and sort of. Like, I totally get where this is going. I just think also that on the flip side, I tend to do this, but like, I think, if the feedback loop between when you write the code first and when you compress it is fast enough, it seems like you're doing it like this. Because it might not take, in this case, it will take a lot longer, I guess, for me particularly, because I don't know the math, and we're doing this very, deliberately while we're building this code. But if you're just, doing a very simple task, like you can probably skip the step of compression and make it to this part, without necessarily breaking things, because we're going to end up, other than the horrible abstract and override and stuff, I'm assuming that we'll have code at least that is going to be similar to each other, and we're going to have the goal being reusable code. We will end up with C# classes or structs that will have reusable code in them and so on. So I think, I guess what I'm trying to say is it's been kind of a long time since I've done abstracts and overrides and virtuals if I didn't have to. So, but I could still be doing object-oriented programming without necessarily using those. I think a lot of people are kind of done with abstract-based classes and that kind of thing. I think it's kind of cool now to do interface-based sort of pseudo inheritance, I guess. Anyway, I don't know what I'm going with that.
That's...
say that we can do it. I'm just saying, if we end up with, we're still going to end up with shape, and we're still going to have a circle that is a shape and a rectangle that's a shape within reason. It might not look the way that you've got it, but we'll still end up with somewhat of a hierarchy of shapes and so on. So I don't think that's the bad part. I think the bad part is probably, to your point, rectangle broke the interface, and now all the other classes have to deal with a design that they don't necessarily need, and then the developer's looking at it going, well, why do I have to pass a shape in to get my circle or to get my rectangle axes when that doesn't apply to rectangle, it only applies to the circle. So that's the kind of thing that you definitely want to avoid, because now you're hiding information and making your and then you're going to have long lists of comments saying, oh, don't use that. And obviously, if you've got code that you have to tell a developer not to use, or a virtual method that throws an exception that says, "Hey, you didn't override this," then yeah, you're in a bad place. But I think you can still kind of like compression. To me, it's very similar. I mean, compression-oriented programming, a la Casey, is still going to end up with you're still driving towards abstraction in that sense, right? And we're still going to end up with probably hierarchies. They're just going to be tighter and cleaner and more purpose-built, I guess.
So you touched on sort of like the core point of this idea, and that is um, the key word here is this one. It's oriented. So the idea behind what we've done is we've started, we just laid out some code that does exactly what we do, only what we do. Whereas in this one, we said we need a shape, and we started with a class shape, and we started expanding on that shape. So where you end up, it's okay. Like this is not the bad bit of object-oriented programming. Like if an object falls out of this process, that's fine. It's not unreasonable to have an object because it's just a collection of values like int foo or whatever that have some meaningful relationships. Like that's an okay situation to be in. But the reason you want to start with this approach rather than this approach is because you might not end up in a situation where you have a class hierarchy, or you might end up in a slightly more sophisticated or simpler, hopefully, end result than just straight up, here's a class, here's a class, here's a class, here's a class. Here's an abstract method, override. You have the potential to end up in a different place if you take this road, whereas this one sort of locks you in early.
And actually, I did a little bit of reading last time after we talked, and in fact, the structive arrays approach, forget the name of the author, the progenitor of that idea. You mentioned his name, but he calls it data-oriented programming.
Oh, Mike Acton.
Yeah. So at the end of the day, it's like, so to reinforce that, it's the output isn't what you're saying is the output isn't important. It's what you're orienting around that's important. So data-oriented programming, it looks at, we're not looking at objects, we're looking at what is the actual data and how does it line up, and you get, structive arrays falling out of that. But again, classes and structs, whatever falls out the other side, it's not the outcome that you care about. It's the process that you oriented around to produce it, and that's what we're talking about.
Exactly. Yes. I'm just thinking, this is great. This is good. This is a good plan, and particularly when you're doing, sort of you want to have this one in mind. I find this is sort of the more practical approach, is this compression-oriented programming. And then you use the data-oriented programming sort of like in the background. It's like, now what's the CPU going to be doing? What's the format of my data? I don't take it as far as Mike Acton does, actually, because I'm not sure. I'm trying to remember what talk it was in, and whether you would have seen it. But one of the pieces of advice he suggests is you should write documentation for your file formats. Which is like that's the sort of level of data orientation that he goes for, is like this is documenting the layout of the data very explicitly, and we've thought very hard about how this data is going to be laid out in memory, and I find personally that is a little bit too constraining to be doing all of the time. And one example of that is perhaps if you look at I'm just trying to think if I have anything available to show off. let's bring up River City on.
I was just thinking about the height map and instructions and the
Yeah.
I remember you did some pixel art in the
Oh yeah, there was
oblique directions and so on.
Heightmap. So I'll open up Heightmap instruction as well. Okay, so we have to serialize these things, and we haven't written a document that documents our data format. Oh look, there's some ASCII art. Where is it? I should probably just search the page.
I do believe
Serialize.
I mean we did publish our formats like sort of in pseudocode, but I don't remember where that is.
Well, exactly. So rather than having a written format, we're just like write that. I
mean, that is like the code is pretty explicit. The code is
pretty explicit,
isn't it? Yeah.
Exactly. So, but we haven't gone and sat down and be like, all right, there's 4-byte count of thing, and then some like and yes, to a certain extent, what we're doing here is self-documenting. But the thing is, we haven't thought about really at all how this is laid out in memory. What we've actually tended to do, and let's see if this Heightmap instruction has one of these. It doesn't, but in this animation serialized context, there's like a version number, and so we're just happy to slap in, if version equals bloody bloody blah. Now, and then write thing depending on whether it's a particular version or not. And so this is sort of really practical, and it lets you move a little bit faster in the realm of reading and writing data types, but
this is specifically for how we're writing storage types, like types intended to be offloaded to like for like in the editor and so on. Whereas I think our runtime, we're doing a totally different thing for serialization, right?
No. Heightmap is
like we're not. I don't think you're calling serialize every like this is part of definition data, so this would have been saved off in an asset file and only loaded one time when the game
yes
loads.
So the actual format of this data is like the members you have here. So we've got we've got this data 2D heightmap data, default height, one way thickness, and then we've got this is editor stuff, but we still keep that around. Excuse me. Okay, so what was I thinking? So we don't really think about how this is laid out in memory, and that's okay because it's like, all right, it's off somewhere else, and we just go in and grab this. We actually do think a little bit about how this is laid out in memory, because as you can see, it's a if we drill down into data 2D, if it's here, if it's not here, I won't. Oh, here it is. This has been carefully made so it is like literally it's an array, and so it's an array with some bounds, and we've thought pretty hard about how this is going to be all localized in memory. But the struct over here, which I was looking at, which was Heightmap, this one is just, we'll just have one of those and some other stuff. Whereas I think if you, this is really, I think, the point, and that is if you go down this road, you're thinking about like struct Heightmap, and then it's like, all right, well, we'll have I forget what this is. It's like, oops.
Fixed layout.
Yeah, it's like layout, explicit or something, and you have to grab like it's just like struct layout, and it's in interrupt. Yeah, it's in interrupts services layout kind dot explicit. Yeah, so and this is actually is it explicit or is it explicit? I think you have to actually label them. I can't remember. But this is kind of the way that C and C++ work, and that is, literally the order of these things that you write them in is how they appear in memory. You can't even do that with a C# class. Like the runtime will decide where these are laid out for you to get better packing and stuff. Whereas this, so you could actually write a struct where instead of where is it? Instead of being like write default height, right one way, right, blah 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 blah, you could go off to the disk and be like, void deserialize, and then something along the lines of return. Oh, it's like map result, and then this is just going to whinge about stuff because it's not in a class. Heightmap result, and then I'm trying to think how I'd do this in C#. Something like result. It's like
is it binary formatter you're looking for? I mean,
no.
That's an interesting thing, that you can actually take the layout of the struct that you've explicitly defined and just blast it all in, like byte for byte from the RAM.
That's basically where I'm going. So it's like byte data equals binary reader dot read bytes size of Heightmap, and then you'd skip this copy, and you do, so you can't really do this easily in C#, but you'd be like read bytes, and then you do something mem copy from data
you have to merge
to result.
You have to interrupt the mem copy bit.
Well, see, what you'd actually do if you were doing this, you'd be like, this br read bytes would be something like, read that many bytes into this pointer. So that's probably.
See, I find this pretty enlightening and pretty like why wouldn't we do that? That seems like a really good idea.
So one really good reason why you wouldn't do this is because it is a versioning nightmare. So if we add a field to this struct, or if we change the order, or if heaven forbid the compiler changes the order of things in this struct, we're going to have a bad time.
The compiler might change the order of the struct even if we are explicitly laying it out?
No, it wouldn't, but you don't want to mess around with that necessarily.
Yeah, I'm starting to think about the idea of what it's sort of like floating point on different platforms. They're in even bigger trouble.
So I guess it's not really a problem, because it's the kind of bug, like if this bug happens, you just be like, the Heightmap's corrupted, so we'll and the whole thing exploded. Where did it explode? Oh, the Heightmap layout changed. And so, it might change because I'm trying to think of actual reasons it might change. It's not going to change unless you make a stupid mistake.
But it is still going. I still can see how, like, before we could have the nice version, like while we're like kind of in line. In this case, we'd have to kind of have like a Heightmap v1 and a Heightmap v2, and then check the version and just grab the whole thing of v1 versus v2, and then it would kind of get out of hand. Exactly,
and that's why we do it this way. So just for people watching on YouTube, what we're talking about is if context.version greater than 3, let's say, then we'll read those things. Just so people watching have an example. And so this is sort of the preferred way of writing stuff. But if you know the memory layout, for example, Has data, bounds data. So this call here, this is a call to write bytes, and if we scroll down here, this is, the read call is literally what we're doing just now, is like read bytes. So we this is like a byte array, so it's like really obvious in this case. But if we want to read like a massive block of data and we know the layout, we can do that really quickly just by dumping it into memory, which is what we do here. So we can use this approach when it's appropriate, but we don't want to use it all the time, for example. And so
that makes sense.
And so and so when you're not worried too much about the performance, those are times where you can be a little bit sloppy about, worrying about the data orientation. You still think about it as you're going, but you don't orient the way you're coding around the data. But it's certainly a useful tool to have in your bag. That's sort of that's the way of thinking about it as far as like trade-offs and stuff go.
Right.
So,
we should code.
Well, we should actually do some coding at some point. That's fine. I did want to have a little talk, and we sort of kind of got into this. Let me look at my list. So the last thing to say about this is how does the compiler do this internally? And I mean, you may already know how this works, so it's probably no big surprise. It's something like, v table pointer foo. So there's this hidden compiler generated pointer off to a v table. So how much are you familiar with how that works?
A little bit. I know about the v table. I know about like call versus callvert. I know it's slower. I know that it generates backing fields for things like properties.
So I will bring this diagram over here. Have you seen this diagram before?
I think I have this in a book somewhere, but I wouldn't say I've looked at it this year at all.
This is drill into the .NET framework internals to see how the CLR creates runtime objects.
I have a book
MSD
called C# via CLR.
Excellent. It should have a diagram very similar to this in it.
Yeah, but I mean, it's been like probably 5 years since I've even looked at it.
So what this is saying is, okay, we've got, if we're over in, class foo, we have, shape, my shape. So this, is a reference to a shape. And the way that's implemented is as a pointer. So this is like stored as, if we're a 32-bit program, x86, this is stored as a 32-bit pointer to the memory of shape, and it points to the type handle. Then, in shape, we've got, we might have, let's not call that foolers. We might have some members like int foo and float bar. If we inherit from this, from rectangle, we might add in float baz, and what comes along is it sort of includes at the top all of this other stuff that was in shape. So you can imagine that, if I was drawing a diagram, this class here, if this is shape, and this is, we inherit from it and we get, so this is why we have, a shape reference, my shape, and, we can, and that will point to a shape. We can then, do a cast to rectangle my rect, and that can point to a shape. And if it knows, which it should, because C# is type safe, it can go ahead and be like, all right, and now I want this bit of data, so it's going to go, it's going to read from shapes. Be like, all right, I want the thing at that offset from, I don't know, I've done that in 2D, which is a bit weird. So it's like, these are the records and I want that one because that's part of the rectangle. So that's maybe our, what was it, float baz. So that's how inheritance works. That makes sense, yes?
Yeah, sure. Yep, absolutely.
And then we have like a v table, but it's actually got a sync block above it in memory, and then this v table. So the type handle is going to point to all of this stuff. There's not just the virtual method table, which is, I don't know, that's the interface table. This is actually apparently changed. This is old, but suffice to say, there's a table and it's got a whole lot of information about what this type is, including where all the virtual methods point to. It looks like they'll be in here. And so you can imagine those are just, I want this method, so give me method 1, 2, 3, 4, depending on whether I call getAxes or, some other virtual method. Okay, so that's how it works under the hood. And so the point of that is, if we end up compressing to something that looks like, oh, I've got a shape that's got a bunch of, abstract methods. If I want a method table, perfect, this is what I'll use. But if I want something different, I can use something different. And what we're going to do is actually something a little bit different. And seeing as we're pretty much spent this entire time chatting about how that works, we won't get too far into it, but let's have a little look-see. So rather than pointing to a virtual method table, one thing we can do is we can be like, let's get rid of that so we can see your screen. Not that we're really going to do much here. So we're going to have struct shape, and we need a way of differentiating between circle and rectangle. And so the simplest thing to do for now would be like enum shape type. Circle, rectangle. And later on, maybe we'll change rectangle into polygon, and hopefully you can see how that that becomes fairly simple. If we end up going with this situation here, maybe we'll have to be something like, we'll have to think harder about that and be like, bool has edges, or has polygon edges, and bool has circle edges, and stuff like that. We maybe we'll do that, but we'll worry about that if we get to that. So shape type, type, and already you can see that this is suddenly like there's so much stuff we can do with this that is different to what we could do with, I deleted all the code, with like an abstract method to get the axes. So I can have an if statement that is like, let's bang it in here, if shape, so type of shape equals type of rectangle, do a thing, dot dot dot. This code, for example, I think this is I'm trying to remember how this goes. I think this code is actually relatively slow, whereas you can imagine if it's like shape dot type equals shape type dot rectangle.
That's comparing like a byte.
That's going to be like, you're going to really struggle to get something faster than that, for example. I think the type of thing, if the compiler works, this has been a long time since I've fiddled around with this, but if the compiler is going and producing release mode code, doing the type compare is actually reasonably fast. I think what it is if shape is rectangle, this one's a bit slow because it actually has to walk the object hierarchy, because you can imagine like if we inherit from rectangle, this could be a child class of rectangle.
It's too bad the compiler wouldn't just replace that with a check against the type handle itself.
Well,
The int pointer.
the reason it can't do that for the is case is because it doesn't know that you haven't linked in some other assembly that's adding things, and you can vaguely do it if you go class sealed class like that, but there's this because I don't do this very often. I can't remember the exact details, but I believe that if you do a sealed class, there's a whole lot of stuff you'd like it to do optimization wise that it actually can't do for various reasons that I don't remember.
That's fine. That's cool.
Okay, so and you can imagine like this could be a byte. Like we could be like, if
I
we want to,
already did that.
Spiffy. So
Only because I got really used to it during the R series.
I mean, exactly. We use this all the time, and the thing is, if we do this, that's still going to take up 32 bits because 24 bits of padding go in there, just to line up this member on a memory boundary. But if we were going and be like byte, foo, suddenly we haven't increased the size of this thing. This is just 16 bits of padding now. So that gives us the opportunity to do that. And so, okay, we want...
hold on. I mean,
yes.
That's very... I didn't... Sorry, I'm learning a lot here. I didn't know that at all. I didn't know that there was this padding bit. I mean, we just finished describing how the CLR is going to be the one that's going to lay out the struct. So how do I know that the bool or the byte you put in right underneath that is going to be properly put into the padding? Is it we just assume that the CLR is smart enough to pack as much as possible into the layout, or
so in the case of class, because this is different in C#, in the case of class, it will shuffle this around to minimize the padding completely. In the case of struct, it will do exactly what you tell it to do. And the reason for this is it does more or less what C++ would do, because most of the time when they were designing it, it's like if you're using a struct, you're probably interoping with some C++ code, and you want to have the same layout as a C++ compiler would produce. So
it's intrinsic to what a struct is the structure, so therefore the structure is implied to be as written.
Yeah, is that, I mean, like there's layout, let's go over here, class bar, no, struct bar, layout. I don't think, so, yes, sequential. From memory, this does...
That's the default, basically.
Laid out sequentially in the order which they appear exported to unmanaged memory. The members laid out according to this packing is specified in the run pack and can be non-contiguous. So you can actually also specify, what is it? Pack? Oh, is it in here? Pack equals 1, for example. So this byte foo int bar byte baz, I think this won't pack at all. But then if you go and read from this integer, this is now an unaligned read, which can cause issues for performance, and on some CPUs will actually flat out break because it's like you can't read an unaligned integer, although the compiler would probably emit the right code to make this unaligned read not just flat out crash. Whereas the reason that this is, this is the default pack 4, and this is going to be like 24 bits of padding, and then there's going to be 24 bits of padding there, is so that this integer read is going to be aligned to a memory boundary, and that just for CPU related reasons that makes it faster.
Yep.
Where was I going with it? So yeah, sequential is the default, and this is what C++ does. This packing value might be 8 on x86, sorry, x64, I can't remember. Whereas class uses auto, in which case the compiler would probably take this and be like, all right, well, you've got all this padding here. Instead of shoving that there, I'm just going to move that up there for you. I'm not sure it actually does this for structs. Objects defined with this enumeration cannot be exposed outside of managed code attempts. Okay, so it will do that apparently, but if you use this and you try and be like I want a bar pointer or something, the CLR is going to complain, because the CLR goes to a great lengths to ensure that you can't actually determine this layout. And the reason for that is that this layout is entirely specified by the CLR. So if it were to go, if the CLR was like, well, if I was, say, flip these two for whatever reason, the program gets like 25% faster. But if some idiot had gone and like passed a pointer to this out, this auto layout thing out to some unmanaged bit of code, that's going to crash hard because the layout's shifting around. So that's basically how this kind of alignment thing is specified. And then you have explicit, which you have to use, what is it? Offset, field offset. So all right, I want this at position 0, and I want this at position 1, and I want this at position 4 or something. And you tell it exactly which byte you want everything at. One reason you might do this, for example, is in fact if I'm like, all right, I want this layout, and suddenly this bar is overlapping these 2 bytes. One interesting thing you can do with this might be like field offset 0. This is no longer an unaligned read because we're on a boundary. Float foo. And now we can access this value either as an integer or a float. I think we did this somewhere in River City actually. I can't remember where.
That's really interesting.
And so this is getting into what we might do over here. So you can see that, okay, we have type, position, and we might do this a simple way, which would be like radius primary, and then float radius.
I see. But you might want to basically read the same radius as X and Y in the layout.
No, not quite. We're going with something slightly different here. So,
right.
Like the obvious thing here would be like, all right, we'll put that there and be like, bool is integer, and so we can use this if we have a list of values. Is it a float value? Is it an integer value? We can store this in the same array of bar. So bar my values equals new bar 100, and then suddenly it's like we have a list of things that could be floats or could be integers. I wish I could remember where we do this, because I'm pretty sure we actually do this somewhere in River City, and it's totally escaped me.
Bonus for opening next time if we find it later.
So this is what's called a discriminated union, and this is like the simplest version of that. But you can imagine, I don't think, C# doesn't even have the union keyword. If this was C++, you might do it like this. You might union that, and the compiler would do exactly what I was just doing with the explicit layout, like this. And it would just be like, all right, everything in the union, overlap it. But in this case, we actually have to do it manually. So what you can imagine we might have is struct data A is int foo int bar. We might have struct data B. That might be double baz. And so you can see here we've got like completely different data. This is an A, and then we might be like, all right, data A. I'm not sure how this actually interacts with field offset because I haven't done this for a while. Data A, and then data B, and so you can sort of see this is where we might be going with our shape, for example, if we were manually doing this inheritance thing. So you can see how this layout here is kind of like, all right, here's our pointer off to a V table, and then we've done, you know, quote unquote inheritance by being like, all right, we've inherited from bar, and we've got, you know, data A is one branch of that inheritance tree, and data B is a different branch. Do you see how that works?
Mm-hmm.
Yep. So this is the way you might do inheritance in a way that, you know, is custom designed.
What about, sorry, the field offsets didn't change to 8 bytes? Is that because they should have and didn't, or is that because, well, because like foo and bar are both 4 bytes, right?
So yes. So okay. So this is where it gets interesting, and this is where I would, like, if I was actually doing this, I'd actually have to sit down and be like, all right, well, the first thing I would do is like, all right, if I have this class, what does the compiler generate? And I'll just be like, all right, I'll just use the same field offset. I just use what the compiler does, just to be sure. Because you're quite right. Like if I go data A dot foo and bar, that's fine. This is going to be at offset 4, and this is going to be at offset 8, and so those are aligned. Whereas this is a 64-bit value.
Offset 4 is from the bool. Sorry, it's not from the. Yeah. Okay.
So no, offset 4 is relative to this. I mean, this should probably have this here. Otherwise, it might whinge. But yeah, offset 4 is from the start of this struct. Whoops.
Yep. That makes sense.
So this is going to be like at 4, and this is going to be at 8. The problem is this is going to be at 4, but its natural alignment is 8 because it's 64 bits. So I don't know off the top of my head whether that's a problem on an Intel or AMD CPU, for example. Like it could be fine on Intel and you know, a massive problem on ARM, for example. And I don't know off the top of my head if it is. So that's the sort of thing I'd look up if I was doing this sort of thing manually.
Right.
So this is why you get the compiler to do this most of the time. And this is like one of those cases where it starts to become really tricky. This is why I think that the language designers for C# were like, let's just make it explicit, because if you're going around doing like union that and then that, you know, the question is the compiler going to be like, all right, well, this needs to be aligned, so I'm going to, in this case, you know, 4 bytes of padding, whereas this case has no padding, or does this one get, like, does the whole thing get 4 bytes of padding up here? You know, I don't know, and the compiler's not going to tell me unless I, you know, go and use some code to check what it does. That's the C++ case. So that's probably why they just got rid of union altogether, because it does a whole lot of implicit stuff that I sure as hell don't remember what it does. So yeah, that's how you do this manually. And so we're kind of doing it in this case, but in this case it's like, well, we all know that they've all got a position, and you know, we can be like, well, this is you know, radius x, and so we're kind of just cheating it, and then it's like, that's probably
right,
what
we're kind of wasting data now. Like we're allocating.
Yes. I knew there was something else I wanted to mention. I know this has sort of been a very discussion-oriented day today, but that's fine. One really big advantage of doing it this way is now we can go struct array style on this. We can be like, right, let's you know, we've got our situation here. Let's go ahead and be like, shape type types, vector2, positions, and then we could be like float radius primaries, float rad secondaries. And so we're still wasting a little bit of memory here, but all of our accesses over here, if it turns out this is entirely circles, we never even touch this array. We're never worried about the fact that this is a sparse array. Another thing you might do is, and we might end up going down this road if we start adding like polygons and stuff. It's like, all right, int data offset, and then we might just have byte. This is a bit tricky in C# because the type safety is going to get annoying. So we probably have like shape data, and we could just like manually allocate struct circle data. Could be we probably need data offset. Oh, actually, we might not need length. We could store length in here. So you can imagine that if we have just shape data and an offset into it, this could be radius float, and then we might have rectangle data. What would this be? This would be like float radius x, radius y. But then if we have like struct polygon data, suddenly we need to have like an what's the syntax for this? Something like stack alloc vector2 vertices. I think you have to specify count somewhere, and be like int count. And so what you'd actually do is there's no real way to express this in C#, like length, a variable length array. You do this a fair bit more often in C++, certainly back in the old days. And so it's like, all right, we're going to allocate some stuff in our shape data, and it's just going to be however long we want it to be. Does it make sense how that works?
Yeah, I mean, I wish we had that, but I guess we'd end up with a mutable struct with a list in it if we tried to do that in C#. Because we could technically, I guess, pretend we have a variable length array by creating a list which will internally resize itself, right?
So what we want to really be doing, this is why I'm saying stack alloc here. So the way this will look in memory, and this is kind of getting into the data-oriented thing, is like, all right, we have, here's type, da 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 da, and da 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 da, and then we have position, da 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 da, and then we have data, and then we have this other array down here, and it's like, okay, this one's going to be like a circle, so this is going to be like radius. This one's going to be a rectangle, so it'd be like radius x, radius y, and so this, you can imagine that this is like that. And then this one is going to be a polygon, so it's like, all right, we've got like x0, y0, x1, y1, and we've probably got a count somewhere, count over here, and then you can imagine this is quite long, and then we've got the next shape will start here, and so this one's going to point to that offset, and then if we have another shape, it's going to point to that position in this shape data array.
We could still, I mean, like when you said we have the count, so we could still kind of we can still kind of cheat that by some arbitrarily sized array, right? We can just allocate more than we need and then use the length to use it as an offset to run that through.
What am I thinking? I'm not sure I quite understand the question. So Um,
No, I mean, you were talking about, well, you can't do this in C sharp. So like, what are we left with if we want to do that with the polygon
I
data?
think you can. Let me just clear up stack C because this is a thing that they did in like a whole lot of the Windows API, and so where is it? Block. There's examples. This is actually on the stack. Oh, is it not stack alec? Is it? Maybe it's just that. No, it's not that because that's a reference. There is a way in C sharp to explicitly have a. I think it's a variable size struct. It's kind of like string actually. Like this is a struct that is, it's a. Like if I was making a string struct, it's a struct string, and then it would be like int count, and then it would be like character array blah, and that's in after count, not a reference. So that's how string is more or less implemented. Does that make sense?
Mm-hmm.
Yeah. So we can do this. There is a way to do it. I'm just I've forgotten what it is off the top of my head. But you can imagine that what this effectively is, this data offset is pointing into this. We could, if we didn't want these to be contiguous, if we didn't, and maybe we don't, you can imagine that, because this is a contiguous block of memory. You can imagine that we just did something like this. It's like object shape data, and we just allocate these things in, and this polygon data the list vector 2, and we just allocate these things on the managed heap rather than our own block of memory, which could be fine. So you can mix and match these things, and you can imagine this object. We could actually do the inheritance thing like shape data, but we've still got positions and stuff out in this SOA way. So there's lots of different ways we could structure this, I guess, is the point of that discussion. And in fact, it could be the case, if we added polygons, perhaps we'd be like, all right, in the case that this is a polygon, we probably want to do like explicit offset and have, this is there, or and then public list, and this is just going off to a block of memory that has the vertices in it, and so
pointer to, yeah.
So it would, yeah. Sorry.
Sorry, I thought you were lining these up to like overlap them.
Yeah, so I just haven't written that in yet. So I'd be like, all right, field offset.
No. I just meant like I was just counting the bytes. Like the two floats were 4 bytes each, and then the reference to the list was 4 bytes, right?
16. So this is one of the hairy things here. It's like this is only going to work in 32-bit now, rather like this is going to be a massive problem if this reference becomes a 64-bit reference. But like that could be the overlap, for example.
Yeah.
Which is one reason it's like this is why an offset index is often better, because we can just make that a 32-bit integer offset into some other block of memory that we set up, rather than having this being like 32 bits on some systems but 64 bits on others. So that's an example of what can really screw you with like this the automatic layout. It's like the size of a pointer changes depending on what system you're.
Yeah, it's particularly now since like FNA is going .NET standard.
Oh yes.
which with multi-targets, which means you can't, like in the old X and A days, you're kind of like it's going to be x86 no matter what, because X and A is x86. But that's not the case anymore with FNA. It's now compiling in any CPU, so it means you don't get to choose what you have no idea what you could be running on. So
yeah, this is a bit of a weakness of C#, and that is it's got issues with, like, if the size of particularly actually this is not so much a C# issue, because long is always a 64-bit value, but in C++ this could be 32 bits or 64 bits. So it depends. That's the problem we had with like the MP3 interop. Is like, well, on some systems this changes length and there's no way to express that in C#. What was I looking at? I'll worry about that another time. I was going to look at some FNA thing. That's fine. I think we are out of time, but I think that has been a very interesting discussion, if nothing else.
Yeah, I think next time we'll just get right into it, I guess. And
yeah, well now,
unless you wanted me to attempt to do this in my own time, in which case it'll look the same as it does now. There will be effort made and stress created.
No, I think we should maybe look into this together. Do you have any questions before we wrap up?
No, a lot to chew on. To go and rethink how I program everything. But
yeah,
yes.
Well, I mean that's good. So you've got a couple of days to just ruminate on this, and we'll come back and we'll actually just start implementing it, and we'll figure out as we go, which of these methods works, and it's probably going to be the really simple one because we have only 2 shape types for now. But we might expand into something else later, so we have to keep that in mind. All right.
It would be cool to see a triangle. I don't know if that's in our rubric.
We could do a triangle. Triangles. Well, this is the thing. Once we've done that, it's going to be really simple to add a triangle.
That'd be a good reward to see the the benefit of the design, because now that we've compressed circle and rectangle, if we can see a benefit to adding triangle, then I think that'll kind of tie it nicely together.
Excellent. All right. Let's stop the stream. See you, YouTube.